Explain how would you compare between hexagonal close packing and cubic close packing. We are supposed to compare HCP with CCP. And whenever you're asked to compare, usually it's a 2-mark question. So you are expected to give at least 4 points. Not at least exactly 4 points. Don't give more, otherwise they'll cut marks. First point is, it has hexagonal unit cell and it has a cubic unit cell. The shape of unit cell is different. Yes, the shape of unit cell is very, very different. Yes. And then how many molecules, how many atoms or how many spheres are within a unit cell? So Z is equal to 6, or 6 spheres are present. 6 spheres or lattice points or entities in one hexagonal unit cell. And in this case, only 4 spheres, atoms in one unit cell. Anything else? Yes. It represents AB, AB, AB type of packing. But the alternate layers are identical. And this represents ABC, ABC, ABC type of packing. You know, if you forget this, I'll give you a trick. When C comes, here also C comes. When there is no C here, it does not begin with C at least. It could be a trick in case you want to just mug this up. These are some very major differences. When it comes to more points, you could give examples of HCP structure. Some examples of HCP and CCP, yes. Additionally, if you're not interested in giving examples, you could draw their diagrams and show that, see, this is the diagram for HCP and this is a diagram for CCP structure. That also is a very beautiful distinguishing point. So you could do that. I'll just show you. Look at the diagrams. This is a classical breakup of CCP structure and this is a classical breakup of HCP structure. But then, since it's all a little messy, some examples can be given for HCP, like metallic zinc, metallic magnesium. They belong to HCP. Even graphite gives you an HCP structure. CCP, if you want to get the examples of CCP structures, yes, you can very well get them. CCP structure could be gold, silver, copper metals. They crystallize in CCP structure. So yes, the 4th point could very well be this distinction. Additionally, if you just want to drag on, you could give the volumes of unit cell, etc. That really is not a very great thing to say. This is a good answer. How will you distinguish between crystal lattice and a unit cell? Well, that is very interesting and very simple also. Just look at this. This is, if it carries on indefinitely in this direction, this direction, this direction, all these points collected together, they are called crystal lattice. And unit cell is just one portion. If you repeat unit cell, you get actually a crystal lattice, right? So crystal lattice is the superset and unit cell is the most small or the most elementary subset. That, one is whole and one is a part. That is a very clear cut and a very classic distinction between each of them. So if you want to note this point wise, I can give it point wise to you also. So we have, let me write it for you, crystal lattice and unit cell. How do you distinguish? Let's try. first point, it is infinite. Crystal lattice is like a line. It has no beginning, no ending. It's an infinite concept. And unit cell, it is finite. First point, sorry. Then it is the superset. And second point, unit cell is a subset of crystal lattice. Okay. Anything else? If it is infinite, obviously you can't measure its volume. So you can say its size and volume cannot be estimated and its size and volume can be estimated. If unit cell is periodically repeated in space along crystallographic axis without any rotation or without leaving any gaps, I get a crystal lattice. So using a unit cell and by repeating it, I can generate a crystal lattice. If I have a crystal lattice and if I cut a very small portion, in fact the smallest possible portion of it, I could get a unit cell. Yes. So that is why we said this is a subset and this is the superset. So that portion is included there. And as a part of an example, fourth point, you could show this diagram. That this, my dears, is a unit cell. And if I keep on, because practically it is very difficult to keep on making this indefinitely, but then I write it like this. That this expansion continues in all the directions. And this is a crystal lattice. This is the fourth point of distinction, a figure which is very clearly showing what is a crystal lattice and what is a unit cell. How will it distinguish between following pairs of terms, a tetrahedral void and an octahedral void? Now this is a very important question. Why? Because both these voids are very crucial in understanding of solid state. How do we answer this? Let's try to write down the points of distinction. And you must remember these points also very carefully. Tetrahedral void and octahedral void. First of all, it is enclosed between four spheres, entities, and it is enclosed between six spheres, entities. Okay, this is just 4 and this is 6. 4 surrounding spheres must be at the corners of a tetrahedron. And in this case, 6 surrounding spheres must be at the corners of an octahedron. In between the content is the same, so you can fill up the same thing. So it is surrounded by, there are 4 particles arranged tetrahedrally and there are 6 particles arranged octahedrally. Okay, anything else? Well, if spheres touch each other Tetrahedral void shortcut is TV. Octahedral void shortcut is OV. Nah. Size of TV is smaller. And if spheres touch each other, size of OV is bigger. Octahedral voids are bigger and tetrahedral voids are relatively smaller voids, which makes sense. Just 4 and you have 6 particles, so obviously you have more space when surrounded by 6 particles. And how exactly do I get an octahedral void? See, you take 3 particles, arrange them in a triangle, and on the top of that put 1/4 particle. This is how you get a tetrahedral void. This is the method to obtain a tetrahedral void. How do you get, this is the 4th point, please note. And octahedral void, how do you get that? Very stylish. You take 3 particles, arrange them in a triangle just like that. You take 3 more particles, arrange them in the form of an opposite triangle. Like this is a triangle like this, and in this case I get a triangle like this, which is opposite, and put one on the top of the other. You could see one triangle here and the other triangle here. This one is pointing forward, this one is pointing backward. Put one on the top of the other, and the hole between them would be an octahedral void. Wow, that would be the case? Yes, that would be the case. If you want more visualizations, I could give you more diagrams. See, this is a tetrahedral void, and this is an octahedral void, right? But if you have to draw in your notebook, well, I think this is a better diagram. You could draw very clearly this and this and show it. These are the 4 points of distinctions, my dear, between a tetrahedral and an octahedral void.